Up until yesterday, we were focusing on forces, particularly balanced forces. That leads us to Newton's first law, which tells us that an object at rest remains at rest. An object in motion continues in motion in a straight line at a constant speed until acted upon by an unbalanced force. We're talking about balanced forces until yesterday, when we started talking about unbalanced forces. When we have an unbalanced force, we get an acceleration. That acceleration depends upon two things. Tell me what two things it depends upon. What's one of them, Ollie?
One of the things would be how much inertia it has.
Well, in a sense it is, yeah. What's related to inertia, Matt? Let's continue on. Always thought there. Mass, yeah. Mass is related to inertia, and the acceleration is related to mass, but not a direct relationship. It's an inverse relationship. In other words, as m goes up, the acceleration goes down. If m goes down, the acceleration goes up. Okay, if Connor's smart car gets pushed with a certain force, and then whoever else's F350 gets pushed with the same force, then the smart car will accelerate more because the mass is less. The mass is smaller. All right, what else does it depend upon? Matt, back to you. Force, the net force. Okay, again, we're talking about unbalanced forces now. There could be 13 forces acting on this object. It's the net force that we care about, the total unbalanced force that we care about. Remember, up till yesterday, it was balanced forces that we were talking about. Now it's unbalanced forces that we're talking about. There is a net force. There is an unbalanced force. And the acceleration is directly related to that. So unlike the mass, if the force goes up, then the acceleration go up linearly with that. Force goes up by a factor of 4, acceleration goes up by a factor of 4. All right, we know the units for acceleration, right? It's meters per second squared. We've done that quite a bit in our last unit. But there's another set of units that we can now use for acceleration. What are they? Based on what you see up on the board. What else could you also say, Cody, for acceleration? Yeah. We don't have to memorize that, right? We just look at the equation and say, look, force is measured in newtons, mass is measured in kilograms. Acceleration could also be newtons per kilogram. You don't need to worry about converting if you see one of these two, because they both mean exactly the same thing. All right, yesterday you had a couple of questions that you were working on page 149. You guys were okay with these questions, or do we need to go over any of them? They're good? All right, we talked about types of forces after that. If we're going to talk about an unbalanced force, then there must be more than one force acting, and that more than one force, those more than one forces that are acting must be of a specific type. Yesterday we talked about 3 types. The first one we talked about was the weight of an object. Often confused with mass, right? Mass is the amount of matter that we possess, and our mass is the same no matter where we go on Earth, no matter where we go in the universe. I weigh 70 kilograms here in Calgary. I weigh 70 kilograms at the top of a mountain in Banff. I weigh 70 kilograms at sea level in Vancouver. I weigh 70 kilograms if I'm in a submarine underneath the ocean. I weigh 70 kilograms if I'm on the moon, or I'm in a spacecraft, or I'm at the outer edges of the solar system. My mass is 70 kilograms. My weight isn't. My weight changes. How come? Because weight is defined as what? Weight's defined as what, Brandon? Good, it's the force of gravity acting on the object. Now the force of gravity changes depending upon where you are. So the mass is the same here, Banff, Vancouver, bottom of the ocean, moon, out in space. My mass is the same. My weight is different because the force of gravity acting on me is different. Okay, my weight here depends upon whatever gravity is in Calgary. Gravity is slightly different in Vancouver, not much, but slightly different. It's slightly different at the top of a mountain in Banff. It's slightly different at the bottom of the ocean. It's way different out at the edges of the solar system. My weight changes depending upon what gravity is, wherever my location is. Weight is the force of gravity. Because it's a force, it's measured in newtons. Now, normal force, we said that normal force is the force of the floor, the force of the ground, the force of whatever it is that you're on, Whether it's the ground, whether it's the floor, whether it's the roller coaster track, whether it's your car seat, not your car seat like a little, 5-point harness like little kids wear, because you guys don't sit in those anymore, I don't think. But rather the seat in your car, whatever it is that's pushing on you, whatever it is that you're on provides the normal force. We say ground in quotation marks because it's usually the ground pushing on you, not always. Pushing up, it's not always up either, but it's usually up, right? Which way could the ground possibly push on you? Well, if you're standing on the ground like I am right now, then the ground has to push up on you. But it is possible that the ground pushes at a different angle. Like let's say standing on a hill like this, the ground would push like this, 90 degrees to the surface. If I'm on a roller coaster and I'm upside down on that roller coaster, probably want to make sure the wheels are on the track though, I guess. Put the wheels on the track of that roller coaster now. The normal force is pushing actually down. Bottom line is the normal force, whether it's the ground like it usually is, whether it's pushing up like it usually is or not, it's always pushing at 90 degrees to whatever the surface is. That force of the surface you're on pushing at 90 degrees to that surface. You can see in all three of these diagrams, the normal force pushed at 90 degrees. The normal force, and this is important, is also equal to my apparent weight. My actual weight is how heavy I really am. My apparent weight is how heavy I feel. Okay? When I perceive my weight right now, it happens to be the same as the force of gravity. But I'm not perceiving the force of gravity. I'm perceiving the normal force of the floor pushing up on me. When I'm in an elevator and feel heavier or feel lighter if you're accelerating downward, you feel heavier or lighter because of the normal force, not because of the force of gravity. When I'm in a roller coaster at the bottom of a loop and feel 4 times heavier than I really am, which is what's going to happen to you in May when we go on our field trip, experience 4 Gs, 4 times the force of gravity. You're going to feel 4 times heavier, but it doesn't mean you are 4 times heavier. Your actual weight is your actual weight, the force of gravity. It just feels 4 times more because the normal force is 4 times more. We finished off yesterday with friction. We talked about 2 kinds of friction, the resistive force, that force between 2 surfaces that resist motion. The first kind was called static, and the second kind was called kinetic friction. Sometimes you're going to see kinetic friction called dynamic friction. Sometimes I like to call it, even though this isn't really an official name for it, I'll put it in quotation marks to remind you that it's kind of my name for it. I like to call it sliding friction. You'll see why in a few minutes, okay? Static friction is that force of friction that keeps an object from beginning to move. Okay. John's desk right now isn't moving. Okay, it's at rest. The forces acting on it are balanced. If I push on that desk right now and it doesn't move, the forces are still balanced. Well, there must be a force that balances the force that I'm pushing with. That would be static friction. Push a little harder, still doesn't move. Well, the force of static friction must be pushing a little harder, right? Static friction is a kind of a pain in the butt, lazy force. It's that kid in your class from grade 1 through grade 11 maybe that only does what he has to do. He's that kid that is smart enough, but he never works harder than he has to work. He just does the bare minimum. Okay, when I push on John's desk, static friction is that kid. Static friction just pushes as hard as it needs to push in order to balance the force. If I push a little harder, all right, it pushes back a little harder because it pushes as hard as it needs to push to balance it out. I push a little bit harder, pushes harder because it pushes as hard as it needs to push. But at some point, the force of static friction, just like that kid that doesn't really want to do much through school, just does what he barely needs to do. At some point, the force of static friction says, you know what, I've had enough. I don't feel like doing anything else. Gives up, and I win. Okay, I push on his desk with a force that's bigger than the max force of static friction. What happens? It starts moving, and the force of static friction gave up. Right? Kinetic friction, on the other hand, That's the slow and steady, student. Okay, that's a student who is smart, okay, works hard, isn't necessarily able to work to do quite as much as that other student, maybe isn't naturally quite as smart, okay, but still works hard and works consistently the whole time. Okay, once John's desk is moving, it's kinetic friction that's kicking in. Kinetic friction, no matter how hard I push, kinetic friction is always going to push back as hard as it can. It's never going to be like, hey, you know what? I only have to push back with 5 newtons. That's all I'm going to do. Okay, if it can push back with 15, that's what it's going to push back with, no matter how hard I push. Once an object is moving, kinetic friction is always the same. Static friction, on the other hand, is different depending upon how hard I push. Now, Ollie asked a good question a minute ago. Said, is that kind of like you got that dresser in your room, you're trying to move it to the other side of the room, you can't get it moving, so you kind of back up from it a little bit and kind of put your shoulder into it and kind of bump up against it hard, and then it's kind of easier and you just kind of push it at that point? That's exactly what it is. Okay, the force of static friction isn't necessarily bigger than the force of kinetic friction, but the maximum possible force of static friction is. We have to overcome the maximum possible force of static friction. So that can be overcome by putting your shoulder into it and giving it a hard hit. You can't keep doing that to keep it going, but the good news is you don't have to, because once you're dealing with kinetic, the force that's required to push it is less. Okay, does that make sense? Does that answer your question? Okay. All right. Kind of addressed with that question, something that I wanted to talk about here with these little notes that you copied down yesterday. That is that the force of kinetic friction is lower than the maximum force of static friction. So I push on John's desk. Maximum force of static friction on John's desk is 20. Yeah, I push with 5, friction is 5. I push with 10, friction is 10. I push with 15, friction is 15. I push with 22, now it moves. Now it's going to be kinetic friction of maybe 16. We're not saying that kinetic friction is less than all of those forces of static friction. We're saying that kinetic friction is less than the maximum force of static friction of 20. 5 was less than 16, but 20 isn't. Okay, the maximum force is bigger than the force of kinetic friction. Finally, yesterday we left you with a couple of new equations. The first one was for the force of kinetic friction. It looked like this. The magnitude, these little absolute value signs, by the way, represent magnitude only. There's a direction with any force, but this equation isn't going to tell me what it is. It's only going to tell me how big the force is. The force of kinetic friction, the magnitude of the force of kinetic friction, is equal to a constant that we call mu. Stands for the coefficient. In this case, the coefficient of kinetic friction. There are no units. It's not grams, it's not kilograms, it's not newtons. The coefficient of kinetic friction. It is a measure, essentially a measure of how much two things stick together. The coefficient of kinetic friction between ice and rubber is low because they don't stick together very well. The coefficient of kinetic friction between pavement and rubber is much, much higher because they stick together much better. Fn is your normal force. And I'll tell you how to find that in a few minutes. Measured in newtons. My other equation, it's not good enough to say force of static friction because this equation doesn't give me the force of static friction. It gives me the maximum force of static friction. It's equal to the coefficient of static friction times the normal force. What do we know about mu s and mu k? Goes back to the last line on this page, right? If the force of kinetic friction is bigger than the maximum force of static, and so is the coefficient. Have a look at this table up on the board right now. You don't have to copy this down. You don't have to memorize this. Whenever you need the numbers for this, they'll be given to you. But just take a look at values of friction, of coefficients of friction for different materials. Copper on copper is really, really high. If you're trying to stop your car really, really quickly, why wouldn't you use copper on copper in your brakes? Maybe. Well, I don't know if it'll blow up, but Might cause a fire. Okay, might cause a lot of heat, yeah. Too much heat, maybe. If not to cause a fire, copper is pretty... No, in fact, you have to apply less force. You have to push on your brake pedal less to get the same effect. Yeah, copper's pretty malleable, right? And combined with the amount of heat that you get with that much friction, it would probably either melt the copper or at least change the shape of the copper, deform the copper too much that it wouldn't work anymore. You have to replace your brakes every week and a half, right? So it's a trade-off. Okay? You got a lot of friction, but it's not very durable in that context, right? Take a look down the list here. Rubber tire on dry pavement, coefficient of 1.2. That's pretty good. But all of a sudden we go to wet pavement. You guys learn in driver's ed about stopping on wet pavement versus stopping on dry pavement. You got to pay attention a little bit more, right? Because it takes you a lot longer to stop on wet pavement because the coefficient of friction is about half. At the same time, I want you to look at the coefficient of kinetic friction. Look how it's almost always lower than the coefficient of static friction, right? 1.0, 0.38, 0.09. Sometimes it's not much lower, but it's almost always lower. So it's almost always easier to get something moving. Sorry, harder to get something moving than it is to keep it moving because the coefficient of static is bigger than the coefficient of kinetic. All right, again, don't panic about memorizing these numbers. Just be able to use these numbers if they're given to you in a problem. Sorry, one more that I wanted to mention to you. You guys know what synovial fluid is? Yeah? What's synovial fluid? Yeah. Yeah, it's the fluid in your joints, right? If you ever have bone rubbing against bone, that's bad on a number of fronts. Number one, it would be really painful, bone against bone. Number two, it would be noisy, squeak, squeak, squeak. Be annoying, right? Number three, it would make the use of your arm or leg or whatever joint you're talking about very inefficient because it would be so much friction and so much energy lost due to that friction. So we're lucky enough to have this fluid, this lubricant inside our joints called synovial fluid. It's kind of like motor oil. Okay? Motor oil prevents metal from rubbing on metal in an engine. Synovial fluid prevents bone from rubbing on bone. And its coefficient of friction is ridiculously small. We're lucky that it's ridiculously small because it allows us to move very easily without experiencing very much friction at all in our joints. All right, let's take a look at an example on page 185, keeping in mind that whatever numbers we need for coefficients of friction, we can always go back to that table to find. All right, this question says a sled with waxed hickory runners. What does that mean? Hickory is a type of wood, right? They make baseball bats out of hickory. And apparently they make runners for sleds out of hickory, or at least they used to. A sled with waxed hickory runners rests on a horizontal, dry, snowy surface. I grew up on the East Coast. Snow on the East Coast was wet and heavy. We'd get 30, 40, sometimes 50. My parents here a couple of years ago in one storm got 100 centimeters of snow, of wet, heavy snow. Here in Alberta, we get this dry snow. The coefficient of friction is different. If you're a skier, you know this, right? You know that you don't like skiing when the snow is wet, when it's kind of slushy, right? Because you ski a lot better when the snow is dry, because the coefficient of friction is less. We got to figure out or find what the coefficient of friction is for waxed hickory runners in dry, snowy surface. And then we got to calculate the mass of the sled if it takes 46 newtons to get the sled moving. Okay, what kind of a problem we have here? Clearly friction. It's a friction thing because we're pushing on it, it's not moving. We're pushing on it with 30, doesn't move. 40, doesn't move. 45, doesn't move. 46, oh, starts moving. This question is telling us that if we have to apply this much force to get it moving, then that is the maximum possible force of static friction. Right? Remember John's desk? I pushed with 5 newtons, didn't move. 10 newtons, didn't move. 15 newtons, didn't move. 20 newtons, It moves, right? I had to apply 20 newtons or more to get it moving. I had to overcome the maximum force of static friction of 20 newtons. Whenever you get a question that says, here's how much you got to apply to get it moving, that's a maximum force of static friction. What else we got? Waxed hickory runners, dry snowy surface. We're going to use the coefficient of static friction, 0.06. And we want to find the mass here. Well, we know that the force of static friction maximum is equal to mu times the normal force. And we know that most times, we said this when we were talking about the types of forces, most times the normal force is the same as gravity. Remember, most times we said, I feel the same weight as I really am. Most times normal force is the same as gravity. In all the questions we do today, that will be the case. The only time it's not the case is if you're accelerating or you're on a hill. For us today, all the problems will be on a flat surface, and we're not going to be accelerating up or down. The normal force will be the same as gravity. So we're going to say mu is equal to FSF max divided by the normal force, but we're going to say the normal force is equal to m times g. Really, that's gravity, right? But usually the normal force is the same as gravity. So let's see what we got here. 46 newtons divided by, oh wait, we don't want to rearrange that to solve for mu, do we? We want to rearrange it to solve for mass. We're still going to make the same substitution. But we're going to rearrange it differently to solve for mass. It becomes FSF max divided by mu times g. So it's 46 newtons divided by 0.06 times 9.81. Let's do that on the calculator. 46 divided by, let's use some brackets, 0.06 times 9.81. $7.82. How many significant digits should that be? Is that right, 7.82? Seems low. It is low. No. Yeah, I guess that's right. 7.82 kilograms. How many digits should it be rounded to? Kind of a weird one. Remember, that counts now, right? Quizzes, tests, significant figures counts. 78? Is it 78.2? Okay, that sounds better. Yeah. Yeah, no, you know what? Gravity does have a direction, but take a look at up here. The absolute value signs mean magnitude. So although there is a direction, we're not paying any attention to it. So we're just going to make it positive 9.81. 78.2, we're going to round that actually to 8 times 10 to the 1 kilograms. That's weird, right? But why 1 sig fig? Yeah, that's right. If I had 0.0060, numbers after the 6 count, zeros after the 6 count, but numbers zeros before the 6 don't count. That's 1 digit. That's 2 digits. Okay, that's 1 digit. Final answer should be 1 digit. Okay, remember, the question's coming up. Remember, if you're given a force that's required to get something moving, that's the force that's overcoming maximum force of static friction. So we're going to call that FSF max. Right? See what you can do with those two questions, please. And put the table up there so you don't have to keep flipping back. Give you a few minutes to work on those, and then we'll take a look. All right, everybody have a look up here. I want to look at number 2. This one's a little bit different than the example we did, right? Question number 1 said there's an applied force of 24 newtons that's required to get the thing moving. That's the maximum force of static friction. That's the force. If you look at John's desk again, remember I pushed with 5 newtons, 10 newtons, 15 newtons, didn't move. Pushed with 20 newtons, it starts moving. That was the maximum force that friction could push back with. The maximum possible force of static friction, FSF max. Question number 2, that's not the case. Okay, we're saying, okay, if we go back to John's desk again for a second, we're saying in question number 2, look, I'm pushing John's desk with 100 newtons. Doesn't move. Well, in order to know if John's desk moves when I push it with 100 newtons, I need to know if the force that I pushed with exceeds the maximum force of static friction. I don't know what that value is. I don't know what that value is now. We got to calculate that value that we said a few minutes ago was 20 newtons. That's what we're going to do with number 2. Find the maximum force of static friction and then compare it with 125 and see if 125 beats it. If it does, great, it moves. If 125 is smaller than the maximum force, then that stubborn maximum force of static friction wins and it doesn't move. So let's get that value. Let's say FSF max for question number 2 is equal to mu times the normal force. Mu, listen, mu between wet, snowy surface and waxed hickory skis is 0.20. The mass, you guys remember what the mass was from example 3.17? 78.2? That should be kilograms. Times 9.81. What do we get for that value of FSF max? Anybody there? Anybody have that yet? Yeah, Andres? 153 newtons. All right, there we go. So we're saying now, go back to John's desk. We're saying, hey, look, there's something heavier on John's desk. The maximum possible force of static friction now on John's desk is 153. I push it with 125. Does it move? No, it doesn't, because I have to exceed the maximum possible force, and I haven't. So no, it doesn't move, because FSF max is bigger than the applied force. Is that okay? Good. Let's try another one here now. This one says a 1640 kilogram lift truck with rubber tires is skidding on wet concrete. Remember what I said when I was reviewing static friction and kinetic friction? I called kinetic friction dynamic friction, and then I put in quotation marks sliding friction. Whenever an object is sliding, it's kinetic friction. Okay, I like to call it sometimes sliding friction, not because that's a real name for it, but because I think that that helps us remember when we've got kinetic friction. Here we've got a truck that's sliding, that's skidding, that's sliding. That's kinetic friction. We want to know the acceleration of the truck. Well, what do we got here? We got the mass of the truck is 1,640 kilograms. We know that we're talking about rubber tires on wet concrete. Let's go back to our table. Rubber tires on wet concrete, kinetic friction, 0.5 coefficient. And we want to find the acceleration. That's all we got. That's all we got here. Well, let's do what we can. Let's do anything we can here. Okay, the first thing that I'm thinking of is force of kinetic friction is equal to mu times the normal force. Why? Well, probably because I have a coefficient of kinetic friction. Okay, let's get that value. 0.5 times the mass, 1640 times 9.81. Look, that's not what I'm looking for, but it's something. And as long as I'm able to find something, it's better than what I had before. .04, what is it, 8044? All right, suggestion, anybody? I just found the force of friction. How am I going to find out? It was 8044, 8.04 times 10 to the 3 it was. I think that's what it said. Yeah. 8044.2 it should be. Now that I got my force here, what am I going to do?
Could you use that as the FS max?
Nope. Nope, because it's not FSF max. We're not talking about static friction. Remember, it's sliding. And whenever we see sliding or skidding, then it's kinetic friction, right? Yep. Yes. If you see one of these questions, guys, and you want to find the acceleration, 3 words. Use the force. 8044.3 newtons divided by the mass of 1640 kilograms. I'm pretty sure that gives me 4.9. So it's going to round to 5, isn't it? 1 digit? 5 meters per second squared. Or 5 newtons per kilogram. Let's have a look at questions number 1 and 2 on page 187, please.